Okay, so we'll start with the free response. Do you want me to work through all the free response? Yeah, okay. Remember, that's exam 2. Hey, Kinga. It's exam 2. You're going to have this projectile motion problem. I'm just going to change the numbers. Light okay? Can y'all see okay with a light like this? Yeah. Just going to change the numbers. Not going to have part C there, but otherwise it's going to be identical to this. So first, for part A, what is the speed of the ball at the top of the trajectory? Remember, when I have an object that's following a path like this, at the top of the trajectory, that the velocity at the top is entirely in the x direction, and that the velocity in the x direction doesn't change. So part A, I'm really just asking, what is the x component of the initial velocity? That's really all that I'm asking. I have this object, ground level, it goes up, comes back down again, and I want to know what is its velocity at the top of the trajectory, which is to say, what is the x component of the velocity, which is going to be equal to v naught times the cosine of the angle theta, which is 12 times cosine of 60. Going to be equal to 6 meters per second. So that's the answer for that one. That was pretty easy. The second part of this is a little more involved. That is, I want to know what is the maximum horizontal range of the ball. I want to know what is this distance, x. I know that x is equal to vx times t. So I know what vx is, right? Vx is equal to 6. So now I also want to know what t is. So to find t, I have to go through, first, I have to find the time at the top of the trajectory. And to do that, I consider that at the top of the trajectory, that Vy is equal to 0. Okay? So I can say that Vy at the top, which is equal to 0, is equal to V naught y plus Ay times t. V naught y, by the way, is equal to 12 sine of 60. And that's equal to, not 6, excuse me, 10 meters per second. 10 meters per second. I think that's right. 12 sine 60. Yeah, it's 10.4. We'll just say 10. So V naught y is 10 meters per second. So now I have everything I need to find the time. I say 0 is equal to 10 minus, this is 10 also because it's meters, the acceleration due to the gravity, which is 10 meters per second squared, times t top. And then I solve that for t top. Say t top is 1 second. That means at the top of the trajectory right here, that t is equal to 1 second. That means that over here, that t, of course, is 2 seconds. Right. So the t total is 2 seconds. And that's the time that needs to go right here. So if I want to find x, x is equal to vx times t. That is vx is 6 meters per second. That's the same as what I found for the initial velocity in the x direction, times 2 seconds are 12 meters. All right, so that one's a little more involved. I can do that? Yeah, I think you can probably do it. The next one that you're going to see is this number 4, or number, excuse me, number 2. I have this block on an inclined plane. It's being pulled up a rope. Again, you're not going to have part B, but otherwise it's going to be the same, an inclined plane with a frictional force acting on it. Hey, Helen. First thing, draw the free body diagram. I always like to draw the picture. It just helps me to think about what's going on. So I have my normal force right here. Notice the normal force is perpendicular to the surface. Because it's being pulled up the inclined plane, I have a frictional force that's going down. It is possible, I suppose, I don't really remember what I did, but I could have caused it to go down the inclined plane. If it were going down the inclined plane, the frictional force would just be opposite. It would be the opposite direction. And then also, I have a force weight. Since the mass is 5 kilograms, the weight is going to be 50, right? So the force weight is 50 newtons. I just multiplied that 5 kilograms times 10, the acceleration due to gravity, g. Also recognize that this angle right here is 90 minus 30, or 60 degrees. Now, next step, you might do this on the same figure, but just for the sake of this, I'm going to do it separately. I'm going to redraw this with resolved vectors. So I have Fn, I have Fk, I have F over here, and then I have my force weight. This is Fw, or 50 sine of 60. And then this is going to be Fw cosine 60, or 50 cosine of 60. Yeah, give me just a second, okay? This thing is not set up right. My pen is not in sync. Okay, sorry about that. So now I can come back to where I was. So I want to know first what is the normal force of the block. Now that I have this diagram drawn, uh, these next two steps are pretty simple. I know there was a lot sort of going into our free body diagram, but if I want to find the normal force, that is this force, since there's no acceleration in the y direction, I can say that the normal force is just equal to that. If you want an equation, that would be the sum of the forces in the y direction is equal to 0. That is Fn minus 50 sine 60 is equal to 0. So Fn is equal to 50 sine of 60, which is 43. All right, that's the first part. I'm going to ask you, what is the normal force? For part B, oh, and by the way, also, there will be no other vertical forces, so the normal force will just be that y component of the weight. I know that in other problems we can change the forces that are pushing down or pulling up on the object. Not in the case for your exam, for this question. Though you will likely have questions like that in the multiple choice part. We can look at that. And then for the second part, the first step will be to find the kinetic frictional force. Fk is equal to 0.1, that's mu, times the normal force. Let me write that equation or put in the numbers. Mu times the normal force, that's 0.1 times 43, that's 4.3 newtons. That's this force, 4.3. I know that this force is 120, and I know that x component of the weight. So to find the acceleration, I say that the sum of the forces in the x direction equals max. This is what I want to know. That's going to be 50 cosine of 60 plus 4.3 minus 120 is equal to the mass, which is 5 times ax, and I solve that for ax. I think it was like point, I don't remember what it was. It doesn't really matter, but whatever that value is. Right? Just like those. Both of your problems are going to be basically identical to that. I said the way that I might change this is I could change the orientation, flip it around, sometimes the other direction. That just makes this become positive and this become negative. Or I could have made it go down the inclined plane instead of going up the inclined plane. If I do that, then this force, the frictional force, goes over here. Okay? And then, of course, the numbers will change. Good on that, y'all? Knowing how to do these will help you to do better on the rest of the exam. So if you really understand these, it'll help you on the rest of the exam. Let's look at the other two, free response, and then we'll start looking at the multiple choice. You're going to have numbers 2 and 4 for that. With number 2, in this problem, we had a disk that was spinning and a bar that was stationary. So here, omega was equal to 3. Here, omega was equal to 0. And then they combined so that we have the disk and the bar like that, and I wanted to know what rate are they spinning at. We know that they're going to be spinning in the clockwise direction because this one was spinning in the clockwise direction. And I wanted to know what is the final angular speed of that. So you're going to have the same problem. They will be different shapes. I will just give you a heads up that you are going to encounter some spheres on the exam. Maybe on this, yeah, you will see a sphere on this question, but I think also in other questions throughout the exam. Remember, y'all, there are two spheres on that equation sheet, and one of them's hollow and one of them's solid. Make sure that you know which one that you're dealing with. I'll say it explicitly in the problem. Just make sure that you're using the right equation. One's like a 2/5 and one's a 2/3 or something. Just be aware of that you are going to be dealing with spheres. And then maybe, I don't remember, but maybe both of them were spinning in the problem that I wrote for y'all. It doesn't change the way that you work the problem, but it's a little bit different. I'll point out what that is. So here, let's skip right ahead to part B, and the answer to part A will fall out. Part B, it says, what is the speed of the disk after placing the bar on the disk? Well, I'll call this L1, this is L2, and we'll call this L3. That is, L1 is the angular momentum of the disk, L2 is the angular momentum of the bar, and then L3 is the angular momentum of the combined system. So, in order to do this, first we need to know what is the moment of inertia of this. That's going to be 1/2 mr squared. That's 1/2 of 4 times 2 squared. Yeah, 4 kilograms. 1/2 of 4 times 2 squared. That's 2 times 4, that's 8. Here, this is going to be 1/12 mb squared. That's 1/12 of 3 times 4 squared. So make sure you get those dimensions right. They're important. That's 3 times 4 is 12 times 4. So it's just 4. And then the combined moment of inertia is going to be I1 plus I2. That's the 8 plus the 4 is going to be 12. You'll need to do that. Find the moment of inertia of each of the two objects and then add them together. Just like the linear momentum problem we did in exam 2, where the two objects stuck together and moved off at the same speed, the same thing is happening here. You can think about moment of inertia as it's sort of the same as mass. They can add together like mass did anyway. So I get L is equal to I omega. So that's going to be 8 times -3 radians per second. The 8 is this moment of inertia. 3 was given in the problem, this 3 radians per second, and it's negative because it's clockwise. The negative is important, okay, especially if you have another object that's spinning. Plus 4 times 0 is equal to 12, that's the combined moment of inertia, times omega final. So that's omega final equals -2 radians per second. Okay? So some things to point out here, just reiterate this, that in this case, L2 is 0. I don't remember if the second object was spinning, but if it was, you would just put that, it would be a non-zero value here, whatever that angular speed was. And then also be aware that the signs are important. Clockwise is what? Negative, right. And counterclockwise is positive, okay? Also, as I said, spheres. You're going to see spheres in a couple of problems. Make sure you get them right, whether it's solid or hollow. We good on that one, y'all? Yeah, Helen. Multiply by 2. Well, if your moment of inertia was doubling, then you would multiply it by 2. We have seen some, I like to call them relational problems, like what happens if you double your moment of inertia, what happens to omega, right? That's probably what you're thinking. We can see, I think we have. Whereas this case, it's not going to be a doubling, it's going to be an adding together. But what if I doubled my mass? You know, I just multiply it times 2. But really, what I'm doing is kilograms plus 80 kilograms. Okay, we'll look at the multiple choice and see what you're thinking about. But here, you're going to be adding. Okay. So we didn't do A because I said it sort of comes along the way. In this case, the moment of or the angular momentum of the total or of the disk, or the initial angular momentum is that 24 or negative 24 kilogram meter squared per second. Okay. You got that? What A is that initial angular momentum. So for this last one, the first thing, which one is bigger? You have a picture, you look at the levels. If the level here is lower than it is here, then the argon has a higher pressure. Most people got that right. In part B, people missed it for various reasons, or they got half credit for various reasons. I know that P is equal to P naught plus or minus rho GH. Since argon has the higher pressure, this is going to be positive, right? Because P is bigger than P naught, so I have to add the rho GH term to make it bigger, right? So the problem that people had, a couple problems, is some people put 1 here for P naught, maybe because they saw this that was just atmosphere right here. But 1 atmosphere is not the SI unit. 1 atmosphere is equivalent to 1 times 10 to the 5th pascals. Okay? Another mistake that people made is that they didn't get the density right. This is filled with mercury. If I look on my table, I see that mercury has a density of 13,600 kilograms per cubic meter. Another thing that people got wrong, that's G, 10 meters per second squared, is that the H is 92 millimeters, but that's not SI units. 92 millimeters, by the way, pressure is often measured in millimeters, especially in a manometer like this, just because the height of your, I don't know, it seems like it should be in centimeters. Anyway, it's often used in millimeters, like 760 millimeters of mercury. That's atmospheric pressure. You might have heard that number before. So anyway, this should be 0.092. Don't make those same mistakes. Usually if it was just one of those mistakes, I didn't count off, but often students made a couple of those mistakes. Just beware, get your density right. The liquid could change. It might not be mercury, so make sure you take note of that. Make sure you change your units from millimeters to meters. It will be in millimeters. 3 decimal places to the left. 92 millimeters is 0.092 meters. And then also get that sign right. That was a less common mistake. And then I think this was like 112,000 or something like that. You do that in your calculator. That's in pascals or newtons per square meter, or I would have accepted 1.1 atmospheres if you converted it back to atmospheres. All right. Yeah. All right. So, exam 1. Any question about the free response? No? Let's just sort of go up to exam 1. We'll take them exam by exam. So see what questions y'all have. You'll have an estimation problem. You'll have a significant figures problem. You're not going to have a triangle problem, okay, because that's going to come up in some of the later chapters. So I don't usually do triangle problems, but you'll certainly see sig figs and standards. You know, while I asked the standard for the meter here, I could ask the standard for the second or the kilogram. For the meter is the speed of light. For the kilogram, it's Planck's constant. For the second, it's frequency of the cesium atom. You're going to have a conversion factor. See, I had a couple here. If I have 2 questions from a topic, you better believe it's going to be on your final. In fact, I think every topic is on the final. Usually on an exam, I have multiple questions from a single topic. So I think I always chose at least one question from each of those topics. You're going to have a kinematics problem. There were a couple questions here for kinematics. Y'all holler out at me if you want to work through one of these, okay? You're going to see a good mix, I think, of conceptual and calculations that, you know, some of them will require you to use formulae and numbers and your calculator and all that, and others will just be thought questions. But I think there's a pretty good mix of those. Questions on any of these? Y'all holler. You're going to see graphs, both qualitative like this and quantitative like this, where you have to find the slope or the area under the graph. For this one, for example, you had to find the area. For this one, you had to find the slope. You're going to see questions like this where I'm asking you which graph describes the physical scenario. Graphs like this where I'm asking you to describe qualitatively what's happening. I will remind you, if I have a position versus time graph, like for example here at point A, the acceleration at point A here it says is negative. That is a true statement. Remember how we get that? That I have a velocity that is positive right here. So I have a positive velocity, but at point A it goes to 0. That means that it's positive and it's decreasing. And if I have a positive velocity that's decreasing in speed, that means that I have a negative acceleration. But the velocity and the acceleration are in opposite directions. In fact, you know, this graph right here is the same graph for an object that's going up and coming back down again. If I were to plot y versus t for that graph, it would look like that. And we know that in that free fall problem, the acceleration is always negative. By the way, if I had the acceleration down here, what would the acceleration at that point be? You flip that graph, what's that going to be? You know? Well, it was negative, now it's going to be positive, right? For a similar reason. All right. Any particular questions from exam 1? Numbers of those that you want to work? Yeah, number 18, sure. Okay, average acceleration between t equal 1 and 3 seconds. I think there was an average acceleration or average velocity that came up. I don't remember exactly how it was, if it was numerical or conceptual. I always like to draw two dots right there. This is the way I approach average acceleration. Some of you might actually use the formula, and the average acceleration, the formula was like delta v over delta t, and then you would find vf minus vi over tf minus ti, and then you would pull those off. So right here, vf is going to be 3.5, 3.5 minus 2.5 divided by 3, that's tf minus 1. That's 1 over 2, or a half. I don't think of it in that way. I do it, I mean, it's similar, it's the same, I guess. I really do it where I'm just finding the slope of that line. Anytime I'm having average acceleration or average velocity, you just connect the 2 points and you find the slope of the line. That's really what you're doing. But you see, I mean, that's what I did here, right? Rise over run. Delta V is change in y over change in x. There was something about average. I don't remember that it was a calculation. It might have been conceptual, but it would do a similar thing. Oh, that was 17. Oh, no, that was 18. So I was using the graph for 17. Yeah, so if I wanted to find the distance that it travels in 4 seconds, so remember, the slope of a v versus t graph is the acceleration, but the area of a v versus t graph is the distance. And since I'm going from 0 to 4, that's going to be the area of this whole graph. I have to divide it up into several sections. I have a triangle here. Remember, the area of a triangle is 1/2 base times height. It's the area of a rectangle divided by 2, right? So that's 1/2 of the base, which is 2 times 5, which is 5. Here, this is a rectangle, so it's 2 times 2, which is 4. Be careful, y'all, because you do have some graphing questions where you have to extract numbers off of the axes. And just like I did here, the squares, or the axis markers, are not going to be the same on the x and y axes. So don't count the squares, is what I'm telling you. Instead, get the numbers off of the axis. And I did that here. I found the 2, which is the 4 minus 2, and then here the other 2 is 2 minus 0 to find the area of that rectangle. And then this other triangle, it has a base of 2, so that's 1/2 of 2, and a height of 2 to 5, or 3, so that's half of 3. And then I add these three numbers together. 5 plus 4 plus 3 is 12. Yeah, so A is the right answer. Okay? The slope of an okay, the slope of an x versus c is the velocity. The slope of a v versus c is the acceleration, and the area of a v versus c is the distance. Okay, easy. Yeah, we good on this one? 17, 18? All right. Listen, y'all, if y'all need to go, I understand, no offense. I'm planning to be here as long as y'all need me here. But if you need to go, that's okay. And I'll just make sure I get your name when you leave. Okay, so you will have to convert units of powers. There were a couple of these, 10 and 9. We're both converting units of powers. Be really careful. We'll come and do number 10, but just be really careful that when you're doing that you're squaring or cubing or whatever the conversion factor. So for example here, if I were converting, let's just say I was converting let's just say I was converting 10 feet squared to meters squared. For example, that's not this problem, but if I was converting that, then if I wanted to convert that to meters squared, then I would say 1 meter is 3.28 feet. And then I have to square the conversion factor. So be really careful on that. Make sure you're squaring or cubing or whatever the conversion factor appropriately. Here, I wanted to find the volume in cubic centimeters. Well, first of all, I know that a room that's 1,000 cubic meters, this room isn't quite 1,000. What is it? We're at 10, 20, 200. This room is about 400 cubic meters or so. So a room about half the size. I know that in cubic centimeters, it's going to be a big, big number, right? So I can get rid of this one, and even that one. It's got to be A or B, because a cubic centimeter is like that big. And think about this room. It has a lot of cubic centimeters in it. So I'd say 1,000 cubic meters. And then I do my conversion factor. I know that in 1 meter, there are 100 centimeters. But what do I have to do to my conversion factor here? I have to cube it, right? So whatever, I take my Q off of this. I have to do the same thing here. That way, this cubic meters cancels with that cubic meters. That meters, which is now cubed. So I get 1,000 times 100, which is now cubed. That's going to be 10 to the 6, so 1,000. That's going to be 1 times 10 to the 6, 1 times 10 to the 9. Okay? Be careful with that. I wouldn't say it's a tricky question, but often students will forget to cube or to square those conversion factors. And let me tell you this, though. Also, in the problem that I give you, one of the conversion factors does not have to be squared. Okay? Y'all be fine. Once you see it, it'll be fine. But, all right. What else? Yeah. Want to go to exam 2? Or, Caitlin? Yeah. Okay. I always like to just start by writing down everything we know. Right, so I look at the numbers, it's traveling at 24, and I ask myself, what is that 24? Well, I know it's a velocity, and that's my initial velocity. So my initial velocity is 24 meters per second. It begins to brake, so it's slowing down, and it stops. That means that the final velocity is 0 meters per second. So also look for those words that are describing it and think, okay, what variable does that describe? And it stops in a time of 4 seconds. and I'm looking for x. Now I know that x is equal to v naught t plus 1/2 at squared. But notice I don't know the acceleration. However, I can find the acceleration because I know that v is equal to v naught plus at. That is 0 equals 24 plus a times 4. So a is equal to -6 meters per second squared. Which jives with what I think it should be because it's slowing down. It has a positive velocity and it's slowing down. So that should be negative, and it came out to be negative. Now I can take that and determine the distance. That's going to be v naught, which is 24 times 4 plus 1/2 of -6 times 4 squared. 96 minus 348. So A is the right answer. Okay? Exam 2. Equal numbers of questions from each exam. Exactly 10 questions from every exam. You're going to see more projectile motion. In fact, I don't remember which one it is. One of these is on, but these are very similar. You're going to see these conceptual questions, these qualitative graphs, kind of like we saw in chapter 1. You're going to see number 9, this vector question. Remember, it's not going to be the same, but here I would say A and then draw B, but I got to draw 2B because it's 2B, and then the resultant is going to look like that, and so that's B right there. So it'll be similar to that, different vectors, and maybe even a different sum, or maybe even a difference, but it'll be similar to that. Have some conceptual questions like these, about vectors, about forces. Yeah, number 10. A vector 3 cannot be added to a vector 4 so that the magnitude is what? So we had a conceptual question like this on the concept test. You can have two extremes. You can have the 4-unit vector and the 3-unit vector like that, in which case they have a resultant of 7. Or you can have the 4-unit vector and the 3-unit vector like that, in which case they have a resultant of 1. Plus or minus 1, but the magnitude of that resultant has to be between somewhere between 1 and 7. So the answer here is, well, 1, 5, 7, and 3 are all between 1 and 7. So it has to be E. It cannot have a resultant that is 0. That's just not possible. You know, in between here, we have a variety of answers where, like, I could have the 4 and the 3, and, you know, here it would be something different. Well, if it was 90 degrees, right, it would be 5. That would be 5. The other one would be something bigger than 5, 6, or whatever. Okay? Going to have some of these 2D problems. We had a couple of 2D problems. You're going to see one like 15. Yeah. In fact, this question is on there, but I have different statements. Okay? But here, you just go through each statement. If the elevator accelerates downward, the mass of the block decreases. Mass isn't affected by the motion of it, right? The mass is an inherent quality or inherent attribute of the object, so it doesn't affect it. So no, that's not right. If the elevator accelerates upward, the force that he's required to hold up with it is bigger than 100 newtons. Is that correct? Yeah, that is correct. So that's a true statement. And as soon as I get a true statement, I can go and begin to get rid of things. So I can get rid of this one and that one because 1 is listed, and I can get rid of that one because it doesn't list 2. If the elevator is stationary, F is equal to 0. Is that true? Oh, that's not true, because if the elevator is stationary, then it requires a force equal to 100 newtons. So 3 is correct. Oh, so I've already got it now. It doesn't really matter what 4 is, but I'll go ahead and look at it. If the accelerator, oh wait, no. Did I change this? Yeah, it should have been 4, 2, 3, and 4. I must have changed it. I don't remember how that went. But the answer would be 2, 3, and 4. All right? Y'all follow what I'm saying? That if it accelerates downward, then that force is 0. You're in free fall at that point. You're weightless. That's the astronauts. They're constantly in free fall, right? So they're weightless. Yeah. Oh yeah, 3 is false. I'm sorry. Yeah. Be careful on these. But I like these because they are good test-taking skills. I was terrible at standardized tests, obviously. All right, so it's just 2 and 4. So D is the right answer. Okay? All right. And I have one like 15. Any of these that y'all want me to do? Uh-huh. 17. Yeah, so if I have an object that is accelerating downward just in free fall, it would tend to have an acceleration of 10 meters per second squared downward. But in this case, that's not true. So that means that there must be some force acting on it. So I have the force weight, which is 50 newtons. I just got that because it's a 5 kilogram object, 5 times 10 G. It's 50. I know that there's some resistive force. I'll call it the frictional force. It's air resistance, though. And that it's accelerating downward at 8 meters per second squared. That's not a force. I'm just showing the direction of the acceleration. So I can say that the sum of the forces equals ma. That is F minus 50 is equal to the mass, which is 5 times negative 8. And so F is equal to 50, it's 5 times 8, 40 is equal to 10 newtons. So A is the right answer, 10 newtons. I think that one's on the test, actually. But different numbers, so, but a free fall question where you're not accelerating. No, that's not right. It shouldn't be, what's 5 times 8? 40? No, that's right. Yeah, that's right. Okay. Okay, what's up? What's next? Yeah, Ethan. Yeah, so you do have a few formulae that you're going to have the full equation sheet that we had on the last exam, but the things that aren't on there are your trig functions, you know, SOHCAHTOA, quadratic, or not quadratic, Pythagorean theorem, F equals ma, and the frictional force is mu times the normal force. Oh, and then the kinematics equations where V equals V naught plus AT, and X equals V naught T plus 1/2 AT squared. So the kinematics equations are really on there. They're just in their rotational form. And you remember, if you forget what these equations are, remember that where there's theta, that translates into X. Where there's omega, that translates into V. And where there's alpha, that translates into A. So those kinematics equations really are on the equation sheet. I think that's it. Yeah. Mm-hmm. So y'all probably know those. I think you know those. You might not. Yeah, you should know them. Like, yeah, you should really know them at this point. We've used them a lot. Um, right? Know them? Yes. Okay. Helen? Yeah, of course. Just like usual. So they'll go in the order that they appeared on exams 1 through 4. Yeah. So that's good. You might even want to put little check marks in between so you can remember the different chapters, because that'll help you to think about your approach to each problem, right? That's what you're thinking right now, isn't it? Yeah, that's probably a pretty good strategy. Which one? 19. A 10 kilogram stone is initially at rest, accelerated by force 15 newtons. What is its stone's velocity? Might draw a picture. Always like pictures. It's initially at rest. That means that V naught is equal to 0. there's a force of 15 newtons, and it's a 10 kilogram stone. I want to know its velocity. I know that v is equal to v naught plus a times t. I know v naught. I know t is 6 seconds. So I need to know what a is. However, I also know that F equals m times a. 15 equals 10 times a. So a is equal to 1.5 meters per second squared. So now I can plug that in. I get v equals 0 plus 1.5 times 6. That's 9 meters per second. Okay. By the way, I did upload just a bit ago all 4 exams just in one file. So if you want to use that, the PDF, or if you don't have a printer and you want me to print it for you, just come by. I'll print it for you. Okay. Just for practice. I find it's useful on paper to do it on paper since the exam's on paper. All right, we good on this exam for now? We can come back to it if we need to. Go to exam 3. No free. Yeah, no free response. This is work and energy, and rotation, and momentum. So even though we have 3 different topics, still just 10 questions from this. It's a little more difficult to pick the questions for this one. This is all work energy theorem. This is the amount of work that's being done. That work is force times displacement, a units problem. With the units problems, look at the equation for it and just plug in the units that you know, and then find the basic SI units. Then we have momentum problems. There is one like number 9. A lot of people miss number 9, but the key to doing this is to draw the picture yourself. Okay, can we just work it? Yeah, draw the picture. So I have a 2 kilogram block that's traveling to the left at 3 meters per second, and it collides with a 1 kilogram block that's traveling to the right at 4 meters per second. This is a 1 kilogram block. And then in the final scenario, the 2 kilogram block now travels to the left at 2 meters per second. So it slowed down, but it didn't bounce and go back the other direction. And now I want to know what is the speed of the 1 kilogram block. So I have the momentum in this top scenario in the beginning, 1 times 4 plus 2 times negative 3 is equal to 1 times VF plus 2 times negative 2. That's 4 minus 6 is negative 2 equals VF minus 4. So VF is equal to 4 minus 2, or 2 meters per second. That means that it's going to be going 2 meters per second to the right. Because it's positive, so it's going to the right. The hard part on this is just drawing the picture. Be very careful in taking cues. To the left is negative, to the right is positive, and then draw it in the picture. And I would even label those velocities as either positive or negative. I use a pool ball, billiard ball. So it'll look a little bit differently because when we talk about billiard balls, but same. You just have masses that have speed. So. Right? Yeah. 6. A box slides towards you and you stop it. Which of these statements are true? Now, I don't remember if this was on there, but there are quite a few of these statements questions where you have multiple statements. The energy of the box is changed. True? Yeah, it had energy, and then you took away the energy. So yeah, that's true. Because you stop it, that's a true statement. You applied a conservative force. Remember, conservative forces are those forces that don't have any contact. Since you were touching the box, no, not a conservative force. So let's see. 1 is a true statement, so that's right. And it can't be this one, and it's not 2, so it has to be D. You did positive work on the box? No, I did negative work. Did I cause the box to accelerate? Well, this better be right. It is. I caused it to accelerate. Remember, accelerate doesn't mean to speed up. Accelerate means to change the velocity. So I'm slowing it down. That is changing the velocity of the box. A lot of this is just the vocabulary. Do you know the vocabulary? And then part of it is, do you know, the physical concepts? You'll holler. Mm-hmm. Okay, number 11. This is in the momentum section. And so I see force. I'm going to automatically think F is equal to my change in momentum over change in time. Let's just write down what we know. I know that mass is equal to 2, that it accelerates from an initial velocity of 8 to a final velocity of 16 meters per second in a time of 4 seconds. And I want to know what force has caused that. So force is equal to m times delta v over delta t. That's just a rewriting of this because delta p is mass times velocity. That's going to be 2. V is vf minus vi, 16 minus 8, divided by t, which is 4. That's 2 times 8, which is 16 divided by 4, so 4 newtons. Look, y'all, take the time to write these things down, to write down the variable name and the number that's attached to it, and then write the equation, and they do this. I see a lot of students, they just do it in their calculator, and those students, they often get it wrong because they'll make a mistake in their calculator, or they don't see the numbers on the page, and so they're not really thinking it. They're trying to get all those numbers crammed up in their head, and that doesn't work very well. Write them out on the page. That's why you have the page there to write these things down. It will really help you to do better on the exam. All right? Rotation stuff. 13. Okay. Bouncy rubber ball and a beanbag. These two things, remember we talked about the towel, you hit somebody with a towel, that it bounces off, that the bouncing off part is pretty important in the force that's imparted, because that means that you have a V final. And when you have a V final, it causes the change in momentum to be bigger. So the answer here is that the rubber ball will impart the greater force. They don't impart the same force. Again, it comes about because of this equation. F is equal to delta P over delta T. That is M VF minus VI over delta T. If this is 0, that means that this is small. If this is not 0, that means that the force is big. A rebound velocity causes your force to be bigger. Ball, it hurts more than if you get hit by a ball that doesn't hurt. It hits you and falls down, that's much. If it bounces off of you, it's a bigger force. I don't know that this question was on there, but certainly that idea comes up on the exam. All right, rotation, like I said. Number 20, sure. So here, angular velocity. The angular velocity of a rigid body is always the same. So it's the same. Remember, however, that V is equal to omega R. So one way that I could change this is I could say Chad's linear velocity, or just his velocity. What is it? Well, in this case, since he's half the distance from half of R is 1/2, then if it were, let me do it in blue. If this was not angular, it would be 1/2 of prices. So if it was just a linear velocity, it would be 1/2. You follow what I'm saying? The angular velocity on a rigid body is always the same. It doesn't matter where you are on the disk or whatever is rotating. But the linear velocity here is twice the linear velocity here, because you're covering a bigger distance in the same amount of time. Here, it's a lot slower. Here, your linear velocity is 0. You're just standing there. You're spinning around, but you're not going around the circle. All right? Exam 4. Hey, yeah. 18 on exam 4? Okay, so this is similar. So omega is equal to 10 radians per second. And I want to know the speed of the point P. That is, I want to know what V is. So I know that V is equal to omega times R. That's 10 radians per second. Do I know the radius? Yeah, the radius is 7.7 meters times 0.7 meters. And that gives me 10 times 0.7 or 7 meters per second. E. You could have looked at the units too. Notice that this question has mixed units. So since I'm asking for the speed, and I've already been given the angular speed, so it's not asking about the angular speed. The angular speed would be 10 radians per second. It's the linear speed, that is, what is v, this vector v. I can get rid of b and c, because those are actually angular speeds, not linear speeds. Okay? I don't usually mix up units, although I guess I did over here too. I mixed up the units, but I guess I do usually mix up units. But it's not an uncommon thing in standardized tests to mix up the units. They're really testing to see, are you reading and comprehending every little letter and every little word. So I think that's really important. For some of you anyway, that standardized testing is going to be important as you move on to wherever you go, become doctors or pharmacists or whatever, or dentists or whatever. So is that clear? Yeah. Sure. So this is a kinematics problem. Just like before, I find it's useful just to write down all the values. The acceleration is 3 revolutions per second squared. I can tell that from this word and then also the units. It goes to an angular displacement, theta, of 24 revolutions. And I want to know the angular velocity. I want to know what omega is after that. I also know that omega naught is equal to 0. So I remember my equations. They're on your equation sheet. Omega equals omega naught plus alpha t. While I know omega naught, I don't know alpha, oh no, I do know alpha. I don't know t. I know omega naught, but I don't know t. So I need to figure out what is t. And to do that, I can use these two. I can say that theta is equal to 1/2 alpha t squared. I left off that omega naught term, omega naught t, because omega naught's 0. That's 24 equals 1/2 of alpha, which is 3 times t squared. 48 divided by t is equal to 4 seconds. And then once I find that, I can come over here. 0 plus 3 times 4, that's my time, are 12 revolutions per second. So C is the right answer for 7. It's a kinematics problem. So it probably looks really similar to the chapter 2 kinematics problems, except where before we had X and A and V, we have theta, alpha, and omega. Y'all need to go. You go. Okay, I know it's getting late, but I'm here until the last person leaves. Sure, I got everybody. It's okay. Go if you want to go. I'll just make sure I got everybody. I see you later. All right, what else? Chapter 4. You're going to have one of these. I like ranking problems. You're going to have a mix of conceptual. I think you have a torque problem too. I like the arm problem, FYI. Conservation of angular momentum. These are the fluid stuff. This is all fresh. Hopefully this is a little easier for you. Isn't everybody? It's okay. No shame. You have lives, I understand. Bye.
Bye.
Other questions, y'all? Or you want to? Yeah. Are there any chapter 4 questions, though? Chapter 4? Yeah, Alan? Yeah. So number 19 is a stress strain problem. Remember, our stress is force over area, y, delta L over L, or L naught, I think we call it. I want to know its increase in length. That is, I want to know this value. So F is 1960. A, I give you the area, 7.1 times 10 to the minus 6 meters squared is equal to the Young's modulus. That's on your data table. I don't know what that is right off. It's a big number. I'm just going to leave it as a y. Delta L is what I'm looking for, and then L naught is 2 meters. And then you solve for delta L. You want me to do that? Is that okay, or is this good? Yeah. So I'm going to put in the numbers. That's usually what y'all do. So I'll put in the numbers. 1960 divided by 7.1 times 10 to the minus 6. Be careful with your order of operations or use that E button. Otherwise, it'll be wrong. That's 2.76 times 10 to the 8th times 2 divided by y. Let's look up y. Huh? Yeah, do you know what it is? 35 times 10 to the 10th. All right, so that times 2 divided by 35 times 10 to the 10th. And I get 0.0016. That should be 1.6 millimeters, right? To convert that, that's in meters. To convert to millimeters, 1, 2, 3, 1.6 millimeters. Calculator is really important on this one. Make sure you use parentheses around those scientific notation. Otherwise, your order of operations are going to get all wonky. Or use that little second E button. That'll keep your scientific notation together. It'll do the order of operations for you. Bye. Okay? Exam 4, questions? All right, we can go back up to exam 3. Again, if you need to go, that's fine. What in exam 3? Seven? Okay. The energy required to go in the higher speeds is bigger because kinetic energy is equal to 1/2 mv squared. So if I plot kinetic energy versus v, I see that it's a parabola. So moving from this speed to this speed causes a relatively small gain in energy, but moving to the higher speeds causes it to go way up. So since it's quadratic dependence, the bigger speed means a much higher energy. Sure. Yeah, this is a, bye, Matthew. You too. This is a conservation of momentum problem. It's similar to what we've seen before. We have two objects moving and ask what is the final velocity of them. But in this case, the initial is that I just have this raft that has a mass of 100 kilograms. It's drifting at 4 meters per second. That's the initial situation. But then a person jumps onto it so that now the raft has a mass of 200 kilograms, and I want to know what is the velocity. My mass has doubled, so you might right away say, well, the velocity must have halved, which you would be right. My initial momentum is equal to my final momentum. That is 100 times 4 is equal to 200 times VF. So VF is equal to half what it was originally, or 2 meters per second. When my mass goes up by a factor of 2, my speed goes down by a factor of a half. Okay. So I have this boy that's swinging a 2-kilogram stone in a circle. There's my stone. And it says that the stone breaks when the tangential velocity is equal to 4 meters per second. What tension in the string causes it to break? The mass is 2 kilograms, and the radius is 3 meters. So the tension that causes it to break is when, it says that the string breaks when it's going 4 meters per second. What is that tension? That tension is my centripetal force, mv squared over r. And so that tension then is equal to the mass, which is 2, times 4 squared, divided by r, which is 3. That's 2 times 16, which is 32, divided by 3, about 11 newtons. There was a free response on that question, too, that was similar on that exam about centripetal forces. All right, Joe? Okay. So here is the relationship between theta and t. I have alpha t squared. If I double the time, what happens to theta? Well, since it's 2 squared, I'm going to have 4 times the original angle, 4 theta. At the end, John? Okay. All right. I think I'll see.